Dr. Ganesh, and we are from Group 2. And today we will be presenting about our project on predicting diabetes using machine learning. And I'll first introduce my teammate first. So our group members consist of 4 people, which is Amar Farhan, me, Alicia Sofia, as well as Nur Nabiha.
Our project is built on data from the Behavioral Risk Factors Surveillance System, or BRFSS, which is a massive national survey that is collected annually by the CDC. The raw BRFSS data was cleaned and refined based on clinical research, which results in a final set of 23 essential features out of original 300 features. Our project tackles two distinct predictions problems simultaneously using different target variables from the same data set. So the first is a classification problem where we predict the diabetes status with a simple yes or no outcome using models such as XGBoost and ANN. And next is the regression problem. Since BMI is a continuous numerical variable and the key health indicator, we use it as a secondary target to predict its value based on the other features using a decision tree regressor and the ANN. So, in summary, our project has three main goals, which is first to build a model that fulfills classification, regression, and artificial neural network. And next is to identify the most influential risk factors that drive diabetes prediction. And lastly is to ensure models are accurate and ready for analysis. And our next speaker will now detail the methodology that was used in this project, which will explain how we prepare our data for these prediction tasks.
Moving on to our methodology, we adhere to the CRISP-DM framework to structure our project. We started with data understanding, which utilizing the CDC Diabetes Health Indicator datasets, which provided us with over 253,000 clean records and 21 health attributes like blood pressure and cholesterol. For data preparation, a critical step was addressing the imbalance in the data. There were far fewer diabetic cases than non-diabetic one. To fix this, we applied the smooth synthetic minority oversampling technique to balance the dataset, and we also applied the standard scaler to normalize the data for neural network. Our modeling approach was twofold, which is classification, where we compared the XGBoost chosen for its efficiency against an artificial neural network to predict diabetes status, and regression, where we compared the decision tree for its interpretability against the ANN to estimate the BMI. Crucially, our evaluation strategy prioritized clinical utility, where we focus on recall rather than just raw accuracy, because in healthcare, missing a diagnosis is dangerous. Now, let's look at the result for our classification model, specifically focusing on XGBoost, which was our best performer. As you can see in the chart, XGBoost achieved an accuracy of roughly 75%. However, the most important metric here is ROC AUC score, where XGBoost achieved 0.7758, indicating a strong ability to distinguish between diabetic and non-diabetic patients. You might notice that our precision is lower at roughly 0.3. This was a deliberate trade-off. By accepting more false alarm, we were able to achieve a recall of roughly 0.6.
From our XGBoost classifier training, we have classified that these are the top 15 features. The top 6 are general health, difficulty walking, consuming fruit at least once or more per day, BMI times general health, then smoked at least 100 cigarettes during their lifetime, and difficulty walking times general health. Moving on to Model 2, we applied a decision tree regressor to predict BMI. We got R-squared score of roughly 0.15. This indicates that the current tree is only explaining about 15% of the variance in the data, which is quite low. Our RMSE is around 6.0, meaning that our predictions are typically off by about 6 BMI points. If we take a look at the plots, we can see why the low score is obvious. Ideally, these green dots would follow the diagonal blue dashed line. Instead, we see a horizontal clustering pattern. This tells us that the model is underfitting. Um, to summarize, a simple decision tree is not complex enough for this dataset. We likely need to move to an ensemble method like random forest to capture these non-linear relationships. We also identified the feature importance for decision tree regressor. The graph shows the top 15 features. The top 6 are general health, has diabetes or pre-diabetic, high blood pressure, age squared, adults who reported doing physical activity or exercise during the past 30 days other than their regular job times age, and lastly, difficulty walking.
Our third model was the artificial neural network model, which is a deep learning approach that we use here for diabetes classification. So the ANN model, due to its complex nonlinear architecture, it was highly effective at learning and training data, which achieves a training accuracy of nearly 77.65%. However, when tested on unseen data, the validation accuracy has dropped to 69.59%. And this gap between the training and validation score indicates that the ANN had a tendency to overfit. It learned the training data exceptionally well, but it struggles to generalize perfectly to new real world data. So while the ANN did achieve the highest recall in some tests, we ultimately favor XGBoost model because it demonstrated better stability during cross-validation and delivered a higher and more consistent single run test accuracy of nearly 75%. Our third model was the artificial neural network model, which is a deep learning approach that we use here for diabetes classification. So the ANN model, due to its complex nonlinear architecture, it was highly effective at learning and training data, which achieves a training accuracy of nearly 77.65%. However, when tested on unseen data, the validation accuracy has dropped to 69.59%. And this gap between the training and validation score indicates that the ANN had a tendency to overfit. It learned the training data exceptionally well, but it struggles to generalize perfectly to new real world data. So while the ANN did achieve the highest recall in some tests, we ultimately favor XGBoost model because it demonstrated better stability during cross-validation and delivered a higher and more consistent single-run test accuracy of nearly 75%.
Then we evaluated the stability and generalization of our models. For XGBoost, the curve gap narrows, which confirms that our model is generalizing well. Also, the spread for training score narrows, indicating model becoming more stable. However, the cross-validation spread increases, which indicates instability, which meant inconsistent and having low confidence.
Moving on to the learning curve of the decision tree regression, there is a severe underfitting or high bias in the model. So the R-square training score is extremely low, which is at about 0.19, and the model is too simple to effectively predict BMI, capturing less than 19% of the data's variance. And next is there's a measurable 0.0357 performance gap that confirms that the model is overfitted to the training data, which fails to generalize the validation set. And lastly is the validation score spread is much larger than the training spread, which indicates a highly inconsistent and unreliable performance on unseen data. And to ensure our models are reliable and not just a lucky one-time test set, we perform a five-fold cross-validation. So for XGBoost classification, the primary goal is to show very strong performance. And we achieved a mean ROC of 0.8771 across all five polls, and the low standard deviation of 0.0525, which confirms that the model is highly stable and provides a reliable, unbiased measure of its predictive power for diabetes status. However, the results for the decision tree regression task were poor. The model consistently failed to predict BMI, which achieves an extremely low mean of R square of only 0.1507. And the standard deviation here is also very low, which is at 0.0038, which tells us that the model is consistently poor. It is stable, but the wrong kind of stable. So this confirms that the specific regression approach is insufficient for predicting BMI.
Assalamualaikum sir, my name is Ahmad Anas bin Azhar, student ID 22005916. So without further ado, let's discuss why we chose specific models and how we interpreted their performance. Firstly, for classification analysis, we chose XGBoost to predict diabetes and we made a clinical choice. We accepted lower precision, which means we might have more false alarm in exchange for higher recall. So why did we do this? In a medical screening context, missing a sick patient in a false negative is much more worse than running a further test on a healthy one. We also prioritize fairness by treating the training data with smoke to ensure the model was not biased towards the majority class. Secondly, for regression analysis, we chose the decision tree over the neural network. Even though neural networks are powerful, decision trees offer transparency. In healthcare, it is crucial to explain why a prediction was made. And in this analysis also, we noted a low R square score here, which indicates that while the survey data successfully captured general health trends, it lacks the granularity to predict exact BMI values perfectly. And thirdly, for neural network, we chose ANN, neural network analysis. We chose ANN. In classification, it struggled with overfitting, meaning high variance, showing a significant gap between training and validation performance compared to the XGBoost. And in regression, while it was stable, its black box nature made it less suitable for patient risk explanation as compared to the decision tree. Moving on to challenges, mitigation, and conclusion. The first challenge that we faced during this project is class imbalance, as the dataset was heavily imbalanced. The ratio was 5.54 to 1 of non-diabetic cases to diabetic ones, which initially caused the model to be biased towards healthy prediction. So as we mentioned earlier, to mitigate this, we applied smooth synthetic minority oversampling technique, which allowed us to create synthetic samples and balance the training data to a 50-50 ratio. The second challenge is that we dealt with skewed data distribution, specifically the physical health and mental health features that contain extreme outliers. So to mitigate this, we applied log transformation. To this, normalize the distribution of these features, making them more stable for the model to process. And to conclude, we found that our model is not reliable enough for real-world diagnosis, as it only achieves a precision of 30%, which means it creates far too many false alarms. And this failure proved that relying on subjective survey data is not accurate enough for medical decision. Secondly, to fix these accuracy failures, future versions need better data. Therefore, they must replace these survey answers with objective medical data like actual blood glucose levels to achieve the accuracy that we originally aimed for. That concludes our group's presentation. Thank you for your time.